Welcome to the course Excelling with Mathematical Modeling. Today we will be discussing about linear predator-prey model. So, we consider the predator, which is the tiger, and the prey, which is the deer. So, we assume that in a forest you have tigers and you have deer. The tiger kills their prey, the deer, for food, and your Tn and Dn be the respective population of tigers and deer at the end of year n. Now, while constructing the model, we make some assumptions, and the assumptions are as follows. So, deer is the only source of food for the tigers. Okay, there is nothing else, only the deers, and tiger is the only predator for deer. So, it is very well defined that the tigers will eat the deer and deer is the only source of food for the tiger. Now, the deer population will grow exponentially if there is no tiger, and without the deer population, the tiger will die due to starvation. So, that is the second assumption. And the rate at which the tiger population grows, that will increase with the presence of deer population, and the rate at which the deer population grows, it decreases with the presence of tiger population. This is some sort of obvious, because when the tiger will find a deer, obviously it will try to kill it for its food and its population will increase, and at the same time when the deer dies, obviously the population of the deer decreases. Now, let us formulate the model. So, you have T n plus 1, D n plus 1. This is the tiger population and this is the deer population. This is the tiger at year n, the deer at year. Now, without the deer, the tiger will die due to starvation, say at a rate alpha, and with the presence of deer, the tiger will grow, say at the rate of beta. Similarly, in case of deer, if there is no tiger, the deer will go exponentially, say at a rate gamma, and when there will be a presence of tiger, obviously it will eat the deer and hence the deer population will decrease at a rate delta. So, here alpha is the rate at which the tiger population dies if there is no food, in this case deer, and beta is the rate at which the tiger population grows when it comes in contact or when it kills and eats the deer. Similarly, gamma is the rate at which deer population grows if there is no tiger, and delta the rate at which the deer population decreases in presence of tigers. So, these are the 4 parameters alpha, beta, gamma and delta. They has to be positive, and alpha and delta must lie between 0 and 1. So, this is the restriction on the parameters. So, once this model is defined, let us now look into its equilibrium solution. So, the first thing is equilibrium solution. So I have Tn plus 1 equal to Tn minus alpha Tn plus beta Dn, and Dn plus 1 equal to Dn plus gamma Dn minus delta Tn. So for equilibria, there should not be any change from n generation to n plus 1 generation, and hence we take both the values to be T star and D star, and you substitute them here. So you get T star equal to T star minus alpha T star plus beta D star, and D star equal to D star plus gamma D star minus delta T star. This cancels, and you are left with minus alpha T star plus beta D star and minus delta T star plus gamma D star. Both are equal to 0. So you solve this, and if you write it in a matrix form, this will be minus alpha beta minus delta gamma T star D star equal to 0. This is a homogeneous equation because the right hand side is 0, and it will have a unique solution T star equal to 0, D star equal to 0, provided determinant of minus is not equal to 0. So we assume that this is not equal to 0, that is minus alpha gamma plus beta delta is not equal to 0, and then we have a unique solution 0, 0. So 0, 0 is your equilibrium solution. So once you get the equilibrium solution, you now check for its stability. So you have the equation Tn plus 1 equal to Tn minus alpha Tn plus beta Dn, and Dn plus 1 equal to Dn plus gamma Dn minus delta Tn. So the coefficient matrix or the Jacobian matrix in this case will be 1 minus alpha beta minus delta 1 plus gamma. So I can take this is as F1, this is as F2, and your matrix is going to be del F1 del T, del F1 del D, del F2 del T, and del F2 del D at the point T star and D star. And you can see, if you just do this, you will get exactly this particular matrix. So now you have to find the eigenvalue of this matrix, and this will give you 1 minus alpha minus lambda beta minus delta 1 plus gamma minus delta lambda equal to 0, where lambda is your eigenvalue. So we simplify this a little. So we get lambda minus 1 minus alpha beta minus delta lambda minus 1 plus gamma, and this will give lambda square minus 2 minus alpha plus gamma into lambda plus 1 minus alpha into 1 plus gamma plus beta delta equal to 0. So you solve lambda equal to 2 minus alpha plus gamma plus minus square root of b square that is 2 minus alpha plus gamma whole square minus 4 1 minus alpha 1 plus gamma plus beta delta divided by 2. And if you simplify this, this can be written as 1 minus alpha plus 1 plus gamma whole square minus 4 1 minus alpha into 1 plus gamma minus 4 beta delta. So, square root of this and divided by 2. So, this is 2 minus alpha plus gamma plus minus square root of. So, this is just of the form x plus y whole square minus 4xy, which we know as x minus y whole square. So, 1 minus alpha minus 1 minus gamma whole square minus 4 beta delta divided by 2. 1 1 cancels, and you will be getting 2 minus alpha plus delta plus minus square root of alpha plus gamma whole square minus 4 beta delta divided by 2. So, this is the generalized version of the eigenvalues in terms of the parameters alpha, beta, gamma and delta. Let us now see how this will behave if you take the numerical values of the parameters. So, if you put alpha equal to 0.5, beta equal to 0.4, gamma equal to 0.1 and delta equal to 0.17. So, your coefficient matrix or Jacobian matrix is this. You substitute these values and you get 0.5, 0.4, minus 0.17 and 1.1. And your A minus lambda I determinant of this will give 0.5 minus lambda, 0.4 minus 0.17 and 1.1 minus lambda. So, if you solve this, you will get lambda minus 0.5 into lambda minus 1.1 plus 0.068 equal to 0. If you simplify this, you will get 1 minus 1.6 times lambda plus 0.618 equal to 0, and you can solve lambda equal to 0.948 and 0.652. So, as you can see, if one of the root is lambda 1, another root is lambda 2, modulus of them is less than 1. So, this implies 0 is stable equilibrium point. However, if you change the values, say alpha equal to 0.05, beta equal to 0.4, gamma equal to 0.1 and delta equal to 0.05. In this particular case, you will see your coefficient matrix is 0.4, 0.4, 0.5, minus 0.05 and 1.1. And you can easily calculate the eigenvalue to be 1.06 and 0.535. So, if you notice, now your modulus is greater than 1 and 1 is less than 1, which implies the system is unstable at 0, 0. Now, let us look into the numerical solution using Microsoft Excel. We just see that whether our analytical result it matches with the numerical one. So, I open the Excel sheet. I will quickly copy this one. So, you have the N, you have the tiger population and the deer population. So, I start with 0 and the second one will be 0 plus 1 and say I calculate the next 30 values. Okay. So, let us take initial population say 500 and this is 200. So, this is equal to. So, in this particular case, let us start with the first one. Your alpha is 0.5, beta is 0.4, gamma is 0.1 and delta is equal to 0.17. And this is equal to say T0, which is this, plus plus so if you look into this equation, it is Tn plus 1. If I put n equal to 0, this is T1 is equal to T0 minus alpha T0 plus beta D0. So, this is T0 minus alpha multiplied by T0 plus beta multiplied by D0. So, alpha is constant and your beta is also a constant. Similarly, if you calculate the deer population, it is D0, so D1 equal to D0, which is this value, plus gamma times D0. So, gamma multiplied by D0 minus delta times T0. So, G0L8, which is a constant, that is your gamma, and G8, okay, gamma is G7, sorry. So, this will be constant and this is your delta, which is again a constant. So, now I drag these values up to 30 of them and let us now plot them. Just before that, I make the font a bit bigger and in the middle. Go to insert, go to this chart and take this chart. So, I will get it this. We'll change the title linear predator prey model and highlight this series, go to select data, then this series, edit. The first one is the predator and the second one is the prey. Okay. So, if I want to remove the grid lines, I will If I want an access title, I will put it here. So this is your time, or you can put year, and this is your population, and you get this. So you can see that with this parameter values, we have already proved that the equilibrium 0, 0 is stable, and hence if you have started from 500 and 200, it approaches to 0. Now let us see what happens if I change this value to 0.05. And immediately you see that the system becomes unstable and it increases unboundedly from starting from 500 and 200. So this matches which are analytical results. Now quickly, what will happen if I change the initial condition? So this system is now unstable and I am playing with the initial condition. Say I make this 130. Let's see. Okay, still it is unstable and it is increasing unboundedly. How about if I increase them to a very large number of tigers? So you see that again they both goes to 0. So what I am trying to say is, in an unstable condition, if you change the initial conditions, the dynamics changes, because since the system is not stable, it will not reach the equilibrium point always from wherever you start. Let us now go back to the slides. Quickly recapitulate the numerical results. So this is your case 1, where your alpha is 0.5, beta is 0.4, gamma is 0.1 and delta is 0.17. This is the case where 0, 0 is stable, and you see that you have started from 500 and 200 and you reaches the point 0. In the second case, your delta value changes from 0.17 to 0.05, and analytically we have seen that the system is not stable, rather unstable. So again you have started from 500 and 200 and you see that your graph increases unbounded. In the third case, I take T0 equal to say 150, your D remains the same, these values remains the same, which means your system is unstable. And in this particular graph you also see the same thing, you started from 150 and 200 and they increases unboundedly. And finally, I make the initial population of the tigers to be 2300, and you see that both the deer population and the tiger population goes to 0. So it is obvious, because with so many tigers they will eat the deers, and when there is no deer to eat, obviously the tiger population will also die due to starvation. We now modify this linear model in a nonlinear model. So our model is Tn plus 1 equal to Tn minus alpha Tn plus beta times Dn, and Dn plus 1 equal to Dn plus gamma times Dn minus delta times Tn. So to make it nonlinear, we introduce the interaction between the tiger and the deer. So when there is an interaction of the tiger and the deer, obviously the tiger eats the deer at a rate delta, so there was a negative sign, and which is then added up to the population of tiger due to reproduction. So if we now look into this model, our first thing is the equilibrium solution. That means there is no change in the n and n plus 1, and we substitute that to be T star and D star. So you put the value here and you get T star equal to T star minus alpha T star plus beta D star T star. This and this cancels, and this gives T star common minus alpha plus beta D star equal to 0. This gives T star equal to 0 and D star equal to alpha by beta. Now, from this equation, you will get D star equal to D star plus gamma D star minus delta T star D star. So this and this cancels. If I take D star common, I get gamma minus delta T star equal to 0. Now, when T star is equal to 0, we are using this. This will imply, so this part vanishes, gamma D star equal to 0, which will be giving D star equal to 0 as gamma not equal to 0. So 0, 0 is the one of the equilibrium solution. And when we put D star equal to alpha by beta, we get from here alpha by beta into gamma minus delta T star equal to 0, which implies T star equal to gamma by delta. So gamma by delta and alpha by beta is another equilibrium solution. Let's now look into the stability analysis. So I have Tn plus 1 equal to Tn minus alpha Tn plus beta Dn Tn, and Dn plus 1 equal to Dn plus gamma Dn minus delta Dn Tn. So I put some F1 Td is equal to T minus alpha T plus beta dt. So this will give del F1 del T, which is 1 minus alpha plus beta d, and del F1 del D, which is beta t. And I put F2 Td is equal to d plus gamma d minus delta dt. So del F2 del T will be minus delta d, and del F2 del D 1 plus gamma minus delta t. So the matrix A is del F1 del T, del F1 del D, del F2 del T, and del F2 del T. So this is 1 minus alpha plus beta d, this is beta t, this is minus delta d, so 1 plus gamma minus delta d, at the point T star T star. So let's now check the values at the equilibrium points. The first T star D star is the origin 0 0. So if we substitute it here, you will get A equal to 1 minus alpha 0 0 1 plus gamma. So clearly eigenvalues are 1 minus alpha and 1 plus gamma. Now the parameter values alpha, beta, gamma and delta, they are all positive. Alpha, beta, gamma and delta are all positive, and this value is always greater than 1. So if I take modulus of 1 minus alpha, this is less than 1, and 1 plus gamma, modulus of that is always greater than 1. So at the equilibrium point 0 0, this particular model is unstable. Let's check the non-zero equilibrium point. So you have A equal to 1 minus alpha plus beta D star, then beta T star minus delta D star, and 1 plus gamma minus delta T star, where your T star is given by gamma by delta and alpha by beta. So if I substitute 1 minus alpha plus beta, your D star is alpha by beta. Now this is beta into T star, so beta into alpha by beta. This is minus delta into D star, which is gamma by delta, and this is 1 plus gamma minus delta, where T star is gamma by delta. So if I simplify this and this cancels, it is 1, this is alpha, this is minus gamma, and this is 1. So if you want the eigenvalues, is A minus lambda I equal to 0, this will give 1 minus lambda alpha minus gamma 1 minus lambda equal to 0. This will be lambda minus 1 whole square plus alpha gamma equal to 0. And this gives lambda minus 1 whole square is equal to minus alpha gamma, write as iota alpha gamma, and this gives lambda equal to 1 plus minus I square root of alpha gamma. So we have a complex eigenvalue with positive real part. I have to take the modulus of this. Again, you can see that this will be greater than 1, and this alpha, beta, gamma, delta, they are positive and lies between 0 and 1, and hence the modulus of this is greater than 1, and hence this system is also unstable at the non-zero equilibrium point. So this model, the nonlinear one, is not a very good model. As you can see that whatever equilibrium points we have, the whole model is unstable no matter whatever the parameter values are. So summing up, in this lecture we learned about the linear pre-predator model, where 0 0 is the only equilibrium point. We perform linear stability analysis about this 0 0 equilibrium point. Our numerical results matches with the analytical results. We then modify this model to a nonlinear one. Our analysis shows that the model is always unstable, no matter what the parameter values are. In my next lecture, we will be talking about forensic model, which is an application of Newton's law of cooling. Till then, bye-bye.